So good morning, everyone, and welcome to this lecture. This is lecture number 3 in induction EMI, and I think we will be able to wind up this chapter here. We have seen electromagnetic induction. We have seen the different ways in which EMF can be induced. The first case that we saw was EMF getting induced because of changing angle theta. You were rotating the coil, you were changing the angle theta. In the second case, we had seen how you can change the area and change the EMF and induce EMF. We did it by the concept of motional EMF. We saw different cases. V cross B dot dl. We saw that it was scalar triple product. The third case was induced electric field. If only magnetic field is changing with time, the this changing magnetic field with time gives rise to an electric field which is different from the electrostatic field. Do we remember this?
Yes, sir.
On similar lines, whenever we are changing magnetic field with time, as I told you, if you have a solenoid or if you have a coil, how do you change this magnetic field with time? We change this magnetic field with time by simply changing on the current in the coil or current in the solenoid with time. Yes or no?
Yes, sir.
Yes or no? Now, let us say that you have a coil, and now we will make the coil like this. We have a coil, as you can see. This is a coil. The number of turns in the coil are n, and the flux linked through any coil is phi. Do you see this?
Yes, sir.
Now this coil, now up till now what we were dealing with resistances. Now whenever we used to draw resistance, we used to draw it as a straight wire, and we used to write it like this, jig 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 jig. That means it is resistance. Now if this straight wire, if you turn it in this fashion, now what happens if you turn it in this fashion? Whenever you allow current to pass through it, now this current that flows through this coil will create a magnetic field. Yes or no? Current creates magnetic field. Yes or no?
Yes, sir.
If it creates magnetic field lines are passing through this coil. Now this coil has an area. Now when it was a straight wire, the area was very less, the cross section area was very less, but when you turn it into a coil, it has a substantial area. Do you see the area of the coil? If I call A becomes the area of cross section of the coil. Do you see this?
Yes, sir.
Now if there is a current in the coil, that creates a magnetic field, and that now creates a flux in the coil. Now this flux passing through the coil, the total flux that passes through the coil will be n into phi. Yes or no?
Yes.
Now if the current is constant, flux will remain constant. Yes or no?
Yes.
So there will not be any induced EMF in the coil, but still there is a flux linked with the coil. Do we understand this?
Yes, sir.
This flux linked with the coil, if you call it as phi or if you call it as n phi, depending on how you are coiling it, will be directly proportional to the current that flows in the coil. Do we understand this?
Yes, sir.
Because this flux is created by the current. So this flux will be directly proportional to the current, or you can write this total flux n phi as Li, where L is a constant that depends on the coil and its geometry. We will see what all factors L depends on. So L is a constant, or you can write L as n phi by I, or you can write L as n into B into A into cos theta. Here theta is 0 by I, or you can write it as total flux divided by total current. Yes or no?
Yes, sir.
This L is known as the self-inductance of the coil. Do we understand this?
Yes.
This L is known as the self-inductance inductance of the coil. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
Everyone understands this?
Yes,
I'll
sir.
give you 1 minute to note this down. Self-induction. Everyone has understood this?
Yes, sir.
I'll give you 2 minutes to note this down. Now, let us take the second case. Up till now, we have kept the current in the coil constant, therefore the magnetic field in the coil is constant, and therefore the flux linked to the coil is constant, and there is no EMI. Now, if I change the current, and di by dt is the rate at which current is changed, do we understand this?
Yes.
Now, because of this change in current, there will be a change in the magnetic field, yes or no?
Yes, sir.
Because of this change in magnetic field, there will be a change in magnetic flux because there is change in current, yes or no?
Yes, sir.
Because of this change in current, there will be an EMI, that will be an EMF induced in the coil, yes or no?
Yes, sir.
And you can see that this EMF induced in the coil will be directly proportional to the rate of change of current, yes or no?
Yes, sir.
Or you can write it as minus L di by dt. What does this negative sign indicate? This negative sign indicates that
It's moving in opposite direction.
this negative sign is explained by Lenz's law, and it tells us the direction of induced EMF. The negative sign tells us the direction of induced EMF will be such that the direction of EMF would be such that what? The direction of EMF would be such that it opposes the change in current. That is, if current is increasing, it will try to reduce it, and vice versa. If current is decreasing, it will try to increase it. This constant L is known as the self-inductance of the coil. Why it is called as the self-inductance of the coil? Because EMF is induced in the coil because of change in current in the coil itself. This phenomena is known as self-induction. So what is the phenomena of self-induction? What is the phenomena of self-induction? What is the phenomena of self-induction? Can anyone tell me? What is the phenomena of self-induction? Anyone has understood this?
Yes, sir.
What is the phenomena of self-induction? No one can explain. Okay, well done. Have you understood this? Have you understood what I've said?
Yes, sir.
Why are you not able to explain it then? If you're not able to explain, that means you have not understood. It's very simple. So the phenomena of self-induction, when the current in the coil changes, the magnetic flux linked with the coil changes. Due to this change of flux, a current is induced in the coil. According to Lenz's concept, it opposes the change in magnetic flux. This phenomena is called self-induction, by virtue of which coil shows opposition for change in magnetic flux, and it is denoted by the coefficient of self-inductance. L is known as the coefficient of self-inductance, and it tells us the ability or the property of a coil to oppose any change in current through itself. I'll give you 2 minutes to note this down. Then we come to the next case where we have on what all factors does this self-inductance or coefficient of self-inductance of a coil depends on. Well, it depends on three factors. The first factor is it depends on the size, shape, and geometry of the coil. If the coil is big, induction, the coefficient of self-inductance will be more. If it is a square shape, it is a rectangular shape, if it is a circular shape, it depends on it because it depends on the area of the coil. It depends on the geometry of the coil. If it is a triangular shape, it will be different. If it is a square shape, it will be different. It depends on the value of mu, the medium which is surrounding the coil. If you change the medium, the value of L will change. It depends on the number of turns. If the number of turns are increased, definitely the self-inductance of the coil, the coefficient of self-inductance would change. It would definitely increase. Remember, the most important term, L does not depend on current in the coil. You might argue, sir, if you make more current to flow in the coil, more magnetic field will be produced and therefore more flux will be linked. No, that is not the case. L does not depend on the current flowing through the coil. So whatever current you flow, L does not depend on it. I'll give you 2 minutes to note this down. And these are the values of self-inductance for some type of commonly coming geometry. The first one is the induction, the coefficient self-induction of a circular coil, mu naught pi n square r by 2. Do we understand? So it depends on the number of turns, it depends on r, means it depends on radius, and it depends on mu naught. That means it depends on the medium mu naught. If the medium is different, it will become mu naught into mu r. Do we understand this?
Yes, sir.
It is directly proportional to n square and directly proportional to radius. Remember this formula. Then we have a long solenoid or a solenoid. The self-inductance of this solenoid is mu naught into mu r, depending on what is the medium which is inside this, into n square into a by l. N is the number of total number of turns. Remember, n is the total number of turns. If you want to write it in terms of number of turns per unit length, you can write the value of L as mu naught into mu r into n square into a into L. Here this small n will be the number of turns per unit length. Do we understand this?
Yes, sir.
A is the area of cross section of the solenoid. Do we understand? Area of cross section of the solenoid, pi square, pi into r square. Do we understand this?
Yes, sir.
You can also write this L as mu naught into mu r into small n square into V, where V becomes the total volume of the solenoid. Do we understand this?
Yes, sir.
The next formula is the formula for a toroid, mu naught n square r by 2, where n is the total number of turns. You can compare this formula to the formula of circular coil and you will find out both the formulas are same. Yes or no?
Yes, sir.
On the right hand side, you have the formula for a square coil, triangular coil, and cylinders. Remember, these formulas may not come directly, but what you have to remember in all these cases is that this is directly proportional to n square. Do you see this?
Yes, sir.
Directly proportional to n square, and again directly proportional to the radius or the length of the side, or in this case area by length. Do we understand this?
Yes, sir.
So you will have to remember with which term it is directly proportional, and remember in all the cases, as you can see, it is coming directly proportional to n square. There are a lot of questions that have come based on this. I'll give you 2 minutes to note down the values fast. Then this is the next heading that the next question that we are going to do. A current in a solenoid of 240 turns having a length of 12 centimeters and a radius of 2 centimeters changes at the rate of 0.8 ampere per second. Find the EMF induced. I'll give you 2 minutes to give me the answer. So how are we supposed to do this? Anyone, any idea? The EMF induced in the coil will be minus L into di by dt. This is a solenoid. What is the self-inductance of a solenoid? The self-inductance of a solenoid is mu naught into n square into A by L. The value of mu naught is 4 pi into 10 to the power minus 7. N is the number of turns, which is given as 240. Area is pi r square. It is given as 2 centimeters, so you can find out the area. Length of the solenoid is given as 12 centimeters. You can convert it into meters and get the answer. Di by dt is the rate at which current is changed, which is 0.8. You can multiply everything, multiply, divide. I will not get into multiplication and division. So you can just put the values, get the answer and stay happy. I hope you can do this. So when you put the values for all these things which are already given, you will get the answer as 6 into 10 raised to the power minus 6 volts. Do we understand this? Do we understand this? I hope we understand this. Well, let me move on to the next question, and this is the next question that is coming on your screens. A coil has a self-inductance of 2 Henry and a current of 5.8 amperes. What is the flux through the coil? I'll give you 2 minutes to give me the answer. So you have to find out the flux. You had to multiply L by I, and I think you have done it quite fast. Congratulations, everyone. Let me move on to the next question, and I hope that you can do it faster. And this is the next one. The number of turns is made 4 times, keeping the radius of the coil same. Then the self-inductance of the coil will become how many times? I'll give you 2 minutes to give me the answer. I hope you can do it faster.
It depends on n square, no, sir.
L is directly proportional to n square, so it should become 16 times. I hope we understand this, yes or no?
Yes.
Now, let me put this question in this way. A circular coil of self-inductance L is made by a constant wire length. If its number of turns is doubled, what is the new self-inductance? Give you 2 minutes to give me the answer. Length of the wire is constant. This is the wire of length L. Oh, both are L. The length of this wire is small l. If I turn it into a circular coil, the self-inductance of this coil will be mu naught
Pi n square r by 2.
n square pi r by 2. If I say that the number of turns here is 1, number of turn here is 1, so what will be the radius of this coil? What will be the radius of this coil?
R, sir.
We need to take deep breaths. The radius of this coil will be the length of the wire is L. So radius of the wire, if I turn it into a coil, the radius of the wire will be L by 2 pi. Do we understand this?
Yes.
You take deep breaths. So in first case, the inductance is mu naught into N is 1 into pi into L by 2 pi into 2. Now in the second case, the number of turns is made 2. So now the length of the wire L will be 2 pi into R dash multiplied by 2. So the new radius R dash will be equal to
L by 4 pi.
L by 4 pi. Now the new inductance L dash will be mu naught into number of turns has become 2, so it is 2 square multiplied by pi by 2 multiplied by L by 4 pi. 4 and 4 getting cancelled. Now you have to find the relation between L and L dash. What is the relation between L and L dash?
2 times, sir.
2 times, sir. So L dash, the total inductance now becomes 2 times L, and this is how you need to do this question. I hope you have understood this. I'll give you 2 minutes to note this down. Well done, excellent. Now let us move on to the next thing. And the next thing that we are going to see is let's first finish this mutual inductance. Then we will go ahead with the other things. Since we have seen self-inductance, let us now move on to mutual inductance and finish it before going any further. What do you mean by mutual inductance now? Any idea? What would be mutual inductance now? Any idea is good. May be correct, it may be wrong, but idea is what that matters. What would you mean by mutual inductance? If there is any such term. Where's my difference? Do you have any idea? Don't just keep your mouth shut. If you don't have any idea, just tell me, sir, we don't have any idea, so that I can move ahead. No point of giving you 15 minutes and then getting the answer that we don't know anything. Yes, you don't know, you tell me, sir, we have not heard this term. Finish. I'll move ahead.
We don't have any ideas.
Never heard the term mutual inductance? Okay, now instead of one coil, I have 2 coils. You can call the first coil as coil number 1. You can call the second coil as coil number 2. Or you can call the first coil as primary and you can call the second coil as secondary. Now, what will happen if you have current which is flowing in the first coil? Now, because of current in the first coil, you will have flux in the first coil.
Yes, sir.
If you change the current in the first coil, the flux in the first coil will change. EMF will be induced in the first coil. That is known as self-induction. We are done with that. Let us see what happens in the neighboring coil. If you have current in the first coil, you can have flux linked in the secondary coil, second coil. Yes or no?
Yes, sir.
If you change current in the first coil, the flux in the second coil can change. Yes or no?
Yes, sir.
And an EMF will be induced in the second coil because of change in current in the first coil. This phenomena where a EMF is induced in the second coil because of change in current in the first coil is known as mutual inductance. Do we understand this?
Yes, sir.
That's it. So that is the phenomena of mutual inductance. Whenever there is a current flowing in first coil, there is a flux link in the second coil. This phenomena is known as self-inductance. Wherever current is changing in the first coil and EMF is induced in the secondary coil, which opposes the current in the first coil, this phenomena is known as mutual inductance. Do we understand this?
Yes, sir.
I'll give you 1 minute to note it down. Then we come to this heading, coefficient of mutual inductance. Coefficient of mutual inductance. And this coefficient of mutual inductance is denoted by the letter capital M. So now you have one coil which is the primary coil. Do you see this yellow coil, the primary coil?
Yes.
And then you see this pink coil, the secondary coil. The number of turns, flux, area and inductance of the first coil are N1, Phi1, A1, L1, and the number of turns N2, Phi2, L2 and A2 are the terms for the secondary coil. Do we understand this?
Yes.
These two coils are separated by some distance. That distance is known as the air gap. Do we understand this?
Yes.
Because of this air gap, the flux in the second coil is always less than the flux in the first coil. Do we understand that? Because some flux is always lost. Do we understand this?
Yes, sir.
Now, if I flow a current I1 or I in the first coil, flux will be linked in the second coil. Yes or no?
Yes.
The total flux linked in the secondary coil will be proportional to the flux in the primary coil. Do we understand this?
Yes.
Or I can say N2 phi 2 will be equal to M into I1, where this M is known as the coefficient of mutual inductance. Do we understand this?
Yes, sir.
Everyone understands this.
Yes, sir.
So I can write this mutual inductance as N2 phi 2 divided by I1. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
Okay, so let me take this. You just take this out. You just don't write it. You might get confused with it. Do we understand this? This M is known as the coefficient of mutual inductance. We get this?
Yes, sir.
Now, if the current in the primary coil is changed, so that what will happen? The magnetic field in the primary coil and magnetic flux in the secondary coil will change. Yes or no?
Yes, sir.
Because of this flux change in the secondary coil and EMF will be induced in the secondary coil. Yes or no?
Yes,
This
sir.
EMF induced in the secondary coil can be written as minus LdI1 by dt. This EMF is introduced in the secondary coil and therefore it is written as E2. This M is known as the coefficient of mutual inductance. Do we understand this?
Yes, sir.
It's the same thing. But here what is happening is we are doing things in the primary coil and changes are happening in the secondary coil. We understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Then we can move ahead and we can see the units and dimensions of M. The units and dimensions of M are going to be same as that of L. Again, the mutual inductance or coefficient of mutual inductance does not depend on the current flowing through the primary. Do we understand this?
Yes, sir.
Then what it depends on? Number one, it depends on the number of turns in the primary as well as the secondary. Do we understand this? It
Yes,
depends on the area of cross section. It depends on the distance between the two coils. It depends on the self-inductance of the two coils. It depends on the medium which is surrounding the two coils. It depends on the orientation, how the coils are there. One coil is here, the other coil is here, or the other coil is here, or the other coil is here. Do you understand this?
yes,
From this orientation also comes a factor which is known as coupling factor, which we will see in the next page. So these are the 7 things on which the mutual inductance depends on. Do we understand this?
yes,
I'll give you 2 minutes to note this down. When we come to the next thing, which is known as the coupling factor, this K is known as the coupling factor, my dear friends, and the value of this K lies between 0 and 1. If K is 1, that means the entire flux of primary coil is linked with the secondary coil, which you can see in this case. In this case, you can see the primary coil is on the top, the pink one, and this primary coil is on the top of the secondary coil. So whatever flux is linked in the primary coil is linked in the secondary coil. Do we understand this?
yes,
If the primary and the secondary coil are separated from each other by some air gap, then the value of this K will not be equal to 1. It will be between 0 and 1, and your mutual inductance will become K times root over L1 into L2. Do we understand this?
yes,
But if your primary and secondary coils are wound in this way, are arranged in this way, are oriented in this way, that the flux in the primary is not going to be linked with the flux in the secondary, in all these cases the mutual inductance and the value of K will be equal to 0. Do we understand this?
yes, sir.
You can also define K as the flux link in the secondary divided by flux link in the primary. We get this? Yes or no? No, yes?
Yes,
Note it down fast. Then we move on and note very quickly the mutual inductance of these 3 types of coil. Here we have 2 circular coils, the inner coil, the pink one, and the outer coil, the green one. Do we understand this?
yes, sir.
Then you have 2 solenoids, the inner one, the pink one, the outer one, the green one. Do we understand this?
Yes,
2 2 square shaped coil. These are the formulas. What you have to remember in these formulas may not be the exact one, but this one, it is proportional to the radius of the inner coil ka square divided by the radius of the outer coil. Here it is proportional to n1 n2 into a by l. Here it is proportional again to the length of the inner coil ka square divided by the length of the outer coil. L, small l is the length of the inner coil and capital L is the length of the outer coil. Similarly, for circular coil, it is r square, small r square, which is the radius of the inner coil divided by the radius of the outer coil. Do we understand this? These are the things that you have to note. We get this?
yes, sir.
Do it fast. Then comes the next heading, whether you have 2 coils in series. Do you understand coils in series?
Yes,
If the coils are put like this, L1 and L2, then the coils are in series. If their mutual inductance is taken as 0, my dear friends, then their total inductance will be equal to L1 plus L2. But if the mutual inductance is not 0, and they carry current both in the same direction. The coils are carrying current in the same direction. Then the total mutual inductance will become L1 plus L2 plus 2M. Do we understand this?
Yes.
If they carry current in mutually opposite direction, one coil has this and one coil has this, then it will be L1 plus L2 minus 2M. Do we understand this?
Yes.
Similarly, if you have two coils in parallel connection, then the formula looks like this. You just need to remember this formula. If it ever comes, then you must be able to write down the value. I'll give you 2 minutes to note this down. Everyone understands this?
Yes.
Then we come to understand the important points, the difference between a resistor and an inductor. If you have a thin wire like this, it will have some resistance. So we draw it like this, but the inductance will be 0 because the area of cross section of this wire is 0. But if you turn this wire in this form, then what will happen? It will have its resistance as well as it will have inductance. Do we understand this? Therefore, this becomes the symbol of inductance, and this remains the symbol of resistance. So you denote resistance by this and you denote inductance by this. Do we understand this?
Yes.
So whenever we have an inductor, this inductor will always have some resistance. Do we understand this? Because this is made up of a wire, and wire always has resistance. Do we understand this?
Yes.
What is the role of L? Inductance is to oppose the change in current. If current becomes constant, then there is no role of L. Do we understand this?
Yes.
What is the role of R? It is to oppose the flow of current. Where up till the time that current is flowing, it will oppose the flow of current always, but inductor will only oppose the change in the current. When the current becomes constant, there is no use of inductance. Do we understand this?
Yes.
Again, we have seen this potential drop across the inductor. We have seen this VA in the direction of current, it is taken as negative. Do we understand this?
Yes.
We have seen this when we were seeing the potential drop across the various elements. Yes or no?
Yes, sir.
VA minus LDI by dt is equal to VV. Do we remember this?
Yes, sir.
Do it fast. Then this is the question. AB is a part of a circuit. Find the potential difference VA minus VB if all the three different cases are given. I'll give you 2 minutes. Will you be able to do this? You've done question like this a lot of times. Yes or no?
Yes.
So what are the answers? In the first case,
8, 9, and 11.
no, these are wrong answers. Okay, so how are we supposed to do this? Current is flowing from here to here. I start from point A. I call the potential as VA. VA. Then I'm moving in the direction of current. So minus L into di by dt. I'm moving across the battery, plus or minus. Everyone has forgotten this. Well done. That is expected from you. So L is 1. I move across the battery. I move from the positive terminal to the negative terminal. Potential drops. So it is minus 5. Then I move across the resistor. The value of the resistance is 2. So minus 2 into I is equal to VB. I hope you understand this. Yes or no?
Yes.
Thank God. So I can write VA minus VB as di by dt plus 5 plus 2I. In case number 1, di by dt is 0. I is 2 amps. So my VA minus VB becomes 9 volts. In case number 2, my di by dt, as you can see, it is increasing. So it is plus 1. Increasing, positive. Current is increasing. Di by dt is positive. Your I is equal to 2. That does not change. So your VA minus VB becomes 9 plus 1, 10 volts. In the third case, my dear friends, di by dt is now decreasing. So it is minus 1. I still remains 2. In this case, my dear friends, the answer that I am going to get is 8 volts. I don't know what you have got, but I hope you have understood how it is to be done. I'll give you 2 minutes to please note it down. If you have any doubts, feel free to ask. Well done. That takes us to the next heading, which is energy stored in the inductor. A capacitor stores energy. An inductor stores energy. How much energy stored in an inductor is given by the formula half Li square, where L is the inductance and I is the current. Now remember, we have already studied two formula. Phi is equal to Li and EMF is minus L di by dt. These are the only three formulas that we have studied in this. Now if I put phi is equal to Li, I can put L as phi by I. So I can write the energy stored in this inductor is equal to half phi multiplied by I. I hope you understand this.
Yes.
I can also write it as half phi square by L. Do we understand this?
Yes.
I know that you have forgotten it, but still I will try my best. If I talk about at this point in time, for the last time, if I talk about energy in a capacitor, I know you have forgotten it. Energy in a capacitor was here it was half Li square. The similar formula was Q square by 2C. Instead of I, you have Q, and instead of L in the numerator, you have C in the denominator, my dear friends. That will be equal to phi into I. Now remember, this phi is doing the same job as V, voltage, because you can see Q is equal to CV is the only formula that we studied here. Q, the job of Q is taken by I. The job of C is taken as by 1 by L. So whatever job this V is doing is to be done by phi. So you can write this formula as phi V I Q half QV. If you remember, this formula can also be written as half QV, or phi square by 2L can be written as half CV square. I hope you are able to understand what I mean to say here. Similarly, if I talk about power lost in resistor, if you remember it, I know you have forgotten it, but still hoping against hope. I square into R. Now remember, the only formula that we did here is V is equal to IR. I, same thing as Q, same thing as I. I don't know how much of this is making sense, but I hope I'm not talking nonsense. Here it is I, here it is C, here it is R, R, C, L. All of these elements coming together nicely. Phi, V, and V, same thing, same, everything same. I don't know how much of this is making sense. It was Q into V, here it was V into I, here it was half CV square, here it was V square by R. If I talk about energy, it was I square RT. Here it was VIT. Here it was V square by R into T. I don't know how much of this is making sense, but here again, I have energy density, my dear friends. Here I have energy density, my dear friends. I know you have forgotten it. Anyone remember this term, energy density?
Yes, sir.
What was that?
Energy per unit area.
As expected, it's wrong. Energy per unit volume, my dear friends. Volume. Energy per unit volume, not area. Here also we had this term of energy density. I know that you have forgotten it, obviously. So anyways, I don't blame you because you cannot forget this habit of forgetting. Anyways, any chance of you remembering this formula, energy density? Any chance? Obviously no chance. Half epsilon naught E square. Was the formula there? Here, my dear friends, it is B square by 2 mu naught. B E epsilon naught in the numerator, mu naught in the denominator. I know it's not making much sense. This is everything that we have done till now in one column, one table. I don't know how much of it this is making sense, but if it is making sense, even if it is making nonsense, please note it down. That takes us to the next heading. It's an RL or a LR circuit. Now this RL or LR circuit, to remind you of something that we had done some time back, I obviously know that you don't remember it. But any chance of you remembering it? This RL circuit is same as what?
RC circuit.
RC circuit. Here we called it the charging and discharging of capacitors. Do we understand this? Now this is similar to charging and discharging of capacitor. Here you have R and L connected to each other. Now, when the switch is closed at time t is equal to 0, remember, when the switch is just closed at time t is equal to 0, do you remember how was capacitor behaving as? At time t is equal to 0. At time t is equal to 0. If I have an RC circuit, at time t is equal to 0, if I have an RC circuit, at time t is equal to 0, if I have an RC circuit, at time t is equal to 0, if I have an RC circuit, at time t is equal to 0, at time t is equal to 0, how does it behave? Obviously, we don't remember it. At time t is equal to 0, how does this circuit behave? How does the capacitor behave? This capacitor behaves as a short circuit. At time t is equal to infinity, this capacitor behaves as open circuit. When the capacitor gets fully charged, it tries to block DC current. You've forgotten it, as expected. Very sad to see, but anyways, we have to move ahead in life. At time t is equal to 0, the RC circuit behaves as a short circuit, and at time t is equal to infinity, it behaves as open circuit. When you come to inductor, as soon as you put the switch on, the current tries to get to the maximum value, but then the inductor will try to oppose it. And therefore, at time t is equal to 0, it behaves as an open circuit. At time t is equal to 0, it is the inverse of capacitor. It behaves as open circuit. Do we understand this?
Yes.
Then what will happen at t is equal to infinity? How will it behave at t is equal to infinity? If you have understood this, then you can tell me that. At t is equal to 0, it is behaving as an open circuit. How will it behave as t is equal to infinity?
Maybe short circuit, sir.
Yeah, so right now note this down. Also note down the behavior of capacitor so that you can compare the two. And you can draw this diagram where you can see at time t is equal to infinity. After a long time, the current will remain constant. When the current remain constant, the inductor will behave as it is not there, and it will just behave as short circuit. Do we understand this? So you can see the difference between an inductor circuit and a capacitor circuit. In a capacitor circuit, at time t is equal to 0, it is behaving as short circuit, and at time t is equal to infinity, it is behaving as an open circuit. But for inductor is actually reverse. At time t is equal to 0, it is behaving as an open circuit, and at time t is equal to infinity, it is behaving as a short circuit. Do we understand this?
Yes.
Note it down fast so that I can give you a question. So how are we supposed to do this? At time t is equal to 0, what will happen?
Current will maximum.
This will behave as open circuit. So the value of I2 will be equal to 0. The value of I will be equal to I1, and that will be equal to, oh sorry, I've written I2 as 0. I should have written I1 as 0, sorry. I1 is the current in the inductor wala branch. I have drawn it wrongly. So this inductor wala branch at time t is equal to 0 will behave as a open circuit. So the value of I1 becomes equal to 0. Your I becomes equal to I2, and that becomes equal to V by R. Do we understand this?
Yes, sir.
At time t is equal to infinity, this behaves as a short circuit. The inductor is not there. So the value of I1 becomes equal to E by R. It is simple. The value of I2 also becomes equal to E by R. They are connected across the battery. The value of I becomes I1 plus I2. So it becomes 2E by R. Do we understand this?
Yes.
Give you a minute to note this down. Now that takes us to the period between 0 and infinity. What will happen between 0 and infinity? The current will grow. So now let us put at time t is equal to 0, you have a switch. The switch is put to position number A. Do we understand this?
Yes.
When the switch is put to switch number A, what will happen will be the growth of current. Do we understand this?
Yes.
And current will slowly try to increase. If I write the current as a function of time, I can be written as V by R into 1 minus e to the power minus RT by L. This is the formula that will come after we solve it. I as a function of time. I as a function of time. Now I can write this formula in this fashion. I can write this as I is equal to I max into 1 minus e to the power minus t by tau. Where how much is I max? I max is actually the current at infinity, and that will be equal to V by R. After a long time, the current will become V by R. Do we understand this?
Yes.
Then this tau will be equal to L by R, and this will be known as the time constant. Do you remember this time constant?
Yes, sir.
What was this time constant? It was the time taken by the charge to become 69% of this. Do we understand this?
Yes, sir.
Time constant, do we understand this? Tau, time constant.
Yes, sir.
It is the time in which the current increases to 63% of its peak value or the maximum value.
Yes.
Everyone remembers this?
Yes.
Then you can also see the graph of this time versus uh, current versus time, and when the current becomes 1 tau, when the time becomes 1 tau, current becomes 0.63 times of I naught. Do we understand this?
Yes, sir.
Everyone gets this?
Yes, sir.
Pakka?
Yes, sir.
Okay. Sometimes you may. Okay, I'll give you time to note this down. Then note down one more thing. Their half-life, capital T. Half-life, capital T, is the time in which the current becomes 50%. And this half-life, capital T, is 0.693 times tau, or it becomes 0.693 times of L by R. It is the time to increase the current from 0 to 50% of its maximum value. Do we understand this?
Yes.
This is known as the growth of current. Current in the LR circuit is growing. Well done. Then you can see when you put, you have seen that I can write this current I as I max into 1 minus e to the power minus t by tau. If I put at time t is equal to 0, the value of current I will be equal to 0, implies the circuit behaves as open circuit. Do you understand this?
Yes.
At time t is equal to infinity, at time t is equal to infinity, this current becomes I max. That implies it behaves as a short circuit. At time t is equal to 1 tau, this current becomes 0.63 times I max. At time t is equal to half-life, this current becomes 0.5 times of I max. Remember this. Do we understand this? Yes or no? No or yes?
Yes, sir.
At the same time, the next important thing that they can ask is the rate of growth of current. Rate of growth of current. When they talk about rate of growth of current, they are talking about di by dt. And whenever they are talking about di by dt, remember this is the derivative of I with respect to time. It will be E by L. E means V by L, e to the power minus t by tau. At time t is equal to 0, the rate of growth of current is maximum and it is E by L. If you don't want to write E, you can write V by L. At time t is equal to infinity, the rate of change of current is 0. Remember these two things. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Well, that was the growth of current. Now what will happen is, if you go back here to the same diagram, what we have done in the first case, what at time t is equal to 0, we put the switch to position number A. So the current in the circuit starts to grow. Do we understand this?
Yes.
Now when it reaches its maximum value, what we are going to do at time t is equal to 0, again we are going to put the switch to position number B. Do we understand this?
Yes.
Now if we switch the switch to position number B, what will happen is that the battery is taken out, yes or no?
Yes, sir.
The battery is taken out and now the current will slowly, gradually become zero. Do we understand this?
Yes, sir.
That process is known as the decay of current, and as you can see, the circuit remains simply like this. Do we understand this?
Yes,
In this decay circuit, you can write the current as I is equal to I max, the maximum value of current, into e to the power minus RT by L, where I max is the maximum current which was there in the which were present in this circuit. I can write this as I is equal to I max e to the power minus T by tau, where tau becomes L by R. Do we understand this?
yes,
And how much would be 1 tau? 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 It would be the time taken for the current to become 37% of its maximum value from the maximum value, and this is how the graph looks like. Do we understand this?
yes,
Everyone understands this?
yes, sir.
If I draw the graph of di by dt, the graph of di by dt also looks same. The first one is a graph of current with time. The second one is a graph of di by dt with time. Do we understand this?
Yes, sir.
At time t is equal to 0, current becomes I max. Do we understand this?
Yes,
At time t is equal to infinity, your current will become 0. At time t is equal to tau, the current will become 0.37 times of I max. Do we understand this?
yes, sir.
At time t is equal to capital T, which is the high half-life, it will become 0.5 times of I max. Do we understand this?
Yes,
The rate of decay of current will be given by E by L into minus T by tau. Do we understand this?
yes, sir.
At time t is equal to 0, di by dt is V by L. Let me write it as V by L. At time t is equal to infinity, your rate of change of current di by dt becomes equal to 0. Is everyone able to understand this?
Yes, sir.
Well done. Again, coming back to the graph of I with t and di by dt, the first two graphs are for current growth. Remember, even in current growth, the graph of di by dt is same as what is the graph for current decay. So remember this, don't get confused. You understand the difference between the two graphs?
Yes, sir.
So remember this graph of current decay, this graph of di by dt is same whether you see it in current growth or in current decay, whereas the graph of current with time in current growth and current decay are different. Do we understand this? Give
Yes,
you a
sir.
minute to note this down. Well done, then this is the first question. Let's see how many of you can give me the reply for this one. LCR Indicate the inductance, capacitance, and resistance. Select the combination which does not have the dimension of frequency. Which one does not have the dimension of frequency? Option 4 is correct. Remember, the time constant for an RC circuit is given by tau. So inverse of it is frequency. The time constant for an LR circuit is given by L by R. So the inverse is frequency. LC oscillation, the time constant is not time constant. 1 by root over LC also has the dimension, root over LC also has a dimension of time constant. The only thing that does not have the dimension of time constant is option 4. Do we understand this?
Yes.
What will be the answer for this one? In a in a LR circuit consisting of an inductance of 8 milliamp Henry and resistance of 4 ohms, what is the time constant?
2, sir.
2 milliseconds. Do we understand this?
Yes.
Questions are pretty simple. If you understand them, the answers would be pretty simple as well. The next one, these are the type of questions that are coming in exam these days. I hope all of you are paying attention to this. An inductor of 20 henries and a resistance of 10 ohms are connected to a battery of 5 volt in series. What is the initial rate of change of current? And the answer is
1 by 4 amps.
1 by 4 R. 1 by 4 is correct. Remember the initial di by dt. Di by dt is E by L. Do you remember this?
Yes.
Just have to divide E by L and you will get your answer. So this finishes this part of the course. We are done with your EMI. As such, we have covered everything that could come into EMI. I'll give you 2 minutes. If there's anything that you want to ask, as doubt, you can ask. Remember, in the next class, we'll be covering a very important chapter which we'll be doing in one class only, and that is AC. So we'll be covering AC and EM waves. And remember, there are 2 questions which are going to come from these 2 topics, which we are going to cover in the next 2 classes starting tomorrow. EM waves, one question is definitely going to come. AC, one question is definitely going to come. And we are going to cover those 2 chapters in the 2 classes that are coming from tomorrow. So I hope that all of you are there in those class. 2 questions straight away you are going to get. 1 question you are going to get from EMI, maybe 2 as well. So if you can just go through the previous 2 more classes, we have covered EMI in 3 classes. You can go back and have a look at the lectures to the 2 classes, the previous 2 classes. This will cover minimum 3 and 4 questions that are going to come. So 4 questions in literally 4 classes. And I hope that you can do this. So be there. In the next class, we will be trying to cover AC and then EM waves. In the 2 classes, we will be also doing questions from the previous year and see what type of questions are coming. So I'll see you. If there's any doubts, you can ask. Else, the class is wrapped up. Take care. God bless you all.